Well, this is John Black, Super Chemist. We're on part 4, a new updated playlist called Time and Time Dilation. And the name of this video is about acceleration and velocity, how they affect time dilation different. And we know this is our photon clock. You can see this guy's he's red, so he's standing still here. It's just going up and down. His photon clock. It's the smallest distance. This information carrier, I keep calling them photons, but that's what I mean, information carriers. When it bounces from here to here, whether it's your synapses from one neuron from the other in your brain, or two atoms in a mechanical clock, or this photon clock, if you're standing still, this is the smallest distance it has to travel. The photon's only moving in the y-axis, the vertical axis. But when you start moving, when you throw your photon off, it can't go up here because by the time it gets here, we're moving. So this plate has moved over to here. You can see it's a right triangle. This is the hypotenuse. That means it's longer than this. And we're only talking about acceleration when you're talking about changing speed. We'll talk about changing direction when we get to the rotating thing, rotation and Earth. Here we're talking about a rocket. You can see plainly when you are accelerating, the line grows. The length of this line, 1 second takes longer because the distance the information carriers have to travel is bigger. But their speed remains constant at c. So you slow down physics. When you're accelerating, your second gets longer and longer and longer, more and more dilated. Now let's say you turned off your rockets somewhere around here, say. Now this is all constant velocity. For the rest of the trip until you turn your rocket around and you do your thrusters, your rocket's thrusters in the opposite direction to slow down. All that time in between you are at constant velocity, constant time dilation, but you have this already time dilated rate that you will keep for the entire trip until you put your rockets on again. Three lines are all constant speed. Do you notice something? The line is not growing or getting shorter. It's remaining constant, just like the speed. Because this line, remember, represents your time. So if this isn't growing or getting shorter, your time is not getting shorter or bigger. And then look what happens when you start going in the other direction. You're actually not going in the other direction, but you're putting your rockets on so you can go slow down, deaccelerate. Look what happens when you deaccelerate. Look at this acceleration. The line gets smaller and smaller until you stand still. This is why I say acceleration changes the flow of time. Time is just an abstract thing, a mathematical construct that represents something. And what it represents is the flow rate of physics. So you're slowing down physics or time as you accelerate. But when you go to constant velocity, you just keep that new, that's what velocity does. It keeps the new flow rate constant. So acceleration doesn't do anything except change the length of this line, which changes the flow rate of information from your information carriers, which slows down the flow rate of physics. But here, you're keeping a constant velocity, you're floating, here you're stuck to something. Here you're stuck to something because there's acceleration. That means anytime there's acceleration, that means there's gravity. Okay, there's no gravity here because it's constant speed. You're floating. See, look down here. This is your photon clock. This is the slowest you are moving because you are standing still. That's obviously the slowest you can move. Each speed correlates to a specific amount of time dilation. And that's dictated by the length of the hypotenuse. Now, if you start moving to the right or to the left, you have to accelerate. You don't just magically go 10 miles an hour, 20 miles. You have to accelerate. That's the first step in time dilation. Without that, you get no time dilation. Keep in mind, this blue line here would actually be like this long. I just made them all the same length so that I could have enough room on my board here. But you can see as you move to the right, just like over here, you move to the right, you're going to make a hypotenuse. You're going to stretch this red line out into a long blue line that's a hypotenuse. And if you keep doing that, accelerating more and more faster, the blue line is going to get faster and faster and faster, just like over here. If you go in this direction, just like over here, it's going to go this way. You're going to get bigger and bigger and bigger and bigger. So you're going to move faster and faster and faster, but look at your time. Your time is the fastest here because your time is based on this distance. And when you're standing still, this distance is the smallest it can be. It can't be any smaller. But when you start moving, accelerating, having more velocity, this line grows and grows. That means it slows down time. Here, your time is running the fastest it can. Here, it's the slowest. You see, it's inverse. Slowest, fastest, fastest, slowest, fastest, slowest. It's inverse to each other. Not because you're going into one dimension and you're going out of another dimension. No, it's because you're speeding up and you're making the photon go more distance. Then, you know, if you got a 50-mile-an-hour route, you deliver a mail or something, and your road is 50 miles, then you're going to be down an hour. But what happens when you can't go that way, and you got to go another way, and that road is 200 miles? You're going to slow down what? Not time. You're going to slow down the flow rate of information. Flow rate of information from the information carriers. And the information carriers are what are they giving you information for? To do physics. The higher speed makes the hypotenuse bigger, stretching out the length or time that a second takes, has to take place. But you can see when you're not accelerating, you're not changing anything. Everything goes back, constant speed, constant time dilation. Acceleration, accelerated time dilation. Accelerated time dilation. Now this is an analogy, so it's not all true, it's just similar. This is a mirror. These 4 black lines are mirrors. If you are standing still, like right here, the blue dot and the red dot will be inside the mirror. The blue dot is the velocity or acceleration. The red dot is time, okay? Velocity and time, or acceleration. This is the smallest distance that your photon or information carrier has to travel. Standing still. What happens if you start moving your velocity or you start accelerating? You come out of the mirror into reality, your velocity or acceleration. What happens to time? Time does the same exact thing, but in the opposite direction. You go up here, your image inside the mirror, which represents time, goes down to here. It does it at the same exact rate. So time slows down at the same exact rate as velocity goes up, but in an inverse direct. Just because something's inverse doesn't mean that there's another dimension, okay? But you can see when you even come out of the mirror more, the time goes out into the mirror more, okay? So you're going up, it's going down. Time is going down as much as your velocity goes up. Same here. You're even out of the mirror more. Your time goes into the mirror even more, into the opposite direction. So you get more velocity, less time. Now, when you are looking in the mirror as a person and you see the other person there, and you're doing this, you accelerate away, and this image of you in the mirror accelerates down. Do you think I'm going into some other dimension? That's why this is all happening. Oh, it's just freaky. No. You're not going into a mirror, less into the mirror dimension and more into the real dimension. No. You're getting further away from the mirror, which means the distance is further. So photons from the light come and hit you, or say a foot, to get from the mirror and get back. Here, it has 2 feet to get to the mirror and get back. Here, it has 3 feet to get to the mirror and back. So you didn't go less into the mirror dimension and more into the real dimension. No, you made the distance in between you and the mirror more, just like this. When you have your photon clock, you're standing still, then you start moving fast or accelerating this way. This is your mirror right here. This is your time. You keep going this way, you get faster, faster. The time goes this way in the same exact acceleration rate, but it's slowing down at the same rate that you are speeding up, just like in a mirror. But that doesn't mean you're going into the mirror dimension. No, 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 no. So you're not going more into the spatial dimension and less in the mirror dimension. Okay? And less into the reality dimension. No, no, it does not mean that. It just means you're making the distance, by moving this way, you make the distance more in between these 2 plates. Because as you're moving, this plate is moving this way. So when you throw an information carrier or photon out, you have a lot longer distance to go. You've stretched out this is a second. You stretched it out. You made a second last longer. Now you might want to see this. They have this flower is a rocket ship, and this heart is the closest sun. And you get in your rocket ship and you go over here to this closest sun. They want you to think that when you're standing still, you're going through some kind of time dimension automatically. You know what I mean? No, there's no time dimension. Time is a freaking abstract noun. That means it's an idea. And then they want you to think, oh, well, when you start going this way, you're going more in space and you're going out of the time dimension. If you're going north and then you start going more east, you're going to go northeast. You're going to go out of the north dimension more and more into the east dimension. They want you to think that you're going to more into the space dimension and less into the time dimension. And then you got to figure out the resultant of these two vectors, you going into this different dimension, and this is your resultant, and this represents you going through space, going from here to here, and you going through time. No. This, okay, represents the photons vector. Both of these are the photons vectors. Stop putting you into the scenarios. You are nothing. What is something is the photon, and it's two vectors in space, not in space and time. Okay, we know that we do this all the time with resultants, and we got an X and a Y component. We never say that they're going in some kind of freaky time dimension. No. This represents the resultant of the vector of the photon, not you. Okay, and this X and Y, that's the component vectors going through two spatial dimensions, not one space and one time. Just like if I was going to my mailbox, and I went this way instead of this way, and using just only the X and Y axes, I do it. Wait, come on, man! We wouldn't say I was going in some other time dimension. Come on. If you move faster, you make the distance in between the plates bigger, and you have you have forced time information carriers to take longer to get the information to do the physics. So you have slowed down physics. You have slowed down a second because you're moving into a spatial dimension, and the photon has to keep up with you, because this Y direction, that's helps you transfer your information, so you don't get any time dilation from that. This horizontal, yeah, you get time dilation because it's not useful. The only thing it's useful for is to keep your photons and information carriers going as fast as you are going this way. It doesn't really help with the transfer of information. See, when it bounces up and down and under the photon, when it was going to go up and down, it was going to do that anyway when you were standing still. That's how useful, because if you went this far from here to this other star in the rocket, right? Well, so did your photons. And if you took your photon clock or your synapses and whatever, your mechanical clocks, yeah, when it bounces back and forth, it got to go like this, right? Boom, boom, boom. Yeah, that's two vectors, but it's the photons vector. It's not your vector going through space and time. It's the photons vector going through X and Y. See, this is why I always say time is a result of something. Yeah, it's a resultant of the photon vectors. It's the two component vectors, X and Y. What about the blue part? This is the constant speed part. You get constant time dilation. See, when you accelerate, you're changing the speed. Yeah, so you keep changing the time dilation. You're floating, so you have different physics than on Earth. But here you have gravity, here you float, here you have gravity. I want you to understand, when you're going at constant velocity, okay, you will never, ever, ever have the same physics as on Earth. I don't care what your velocity is, because you're always floating, okay? But you can have the same time dilation if you're moving at 11,200 meters per second squared, per second, because that's the escape velocity of Earth, okay? So you'll have the same time dilation, but you'll never, ever have the same physics, okay? Over here, you will never, ever have the same time dilation. Never, ever. Because even if you were going at 11,200 meters per second velocity, you're accelerating, so you will only be there for, what, a second? But the physics, okay, as long as you're going at 9.8 meters per second squared, you'll have the same physics as on Earth. Just like here, if you're 11,200 meters per second velocity, you'll have the same time dilation. But other than that, you can never have the same physics unless you're going at this acceleration. Same here, you can never have the same time dilation unless you're going at this exact velocity.